Okay, good afternoon, ladies and gentlemen. My topic for this afternoon will be DC circuit. It's a long video format. DC circuit lesson number 17. This is a very important topic on long video format. So for those who are taking up electrical engineering, or for those people who would like to learn electrical engineering, this is for you guys. This is now a combination of the so-called superposition versus the so-called Thevenin theorem. My main topic actually on lesson number 16 is actually superposition theorem. Superposition theorem. I have given you an example problem on the computation of a current on a certain part of the circuit by using superposition theorem. With the given condition, there are two voltage sources. Okay, so for today, this afternoon, it's September 2, Labor Day. We will be comparing the answer from the previous lesson number 16 to this new topic now. It's not a new topic. We are just checking the validity of the answer on the superposition theorem by using Thevenin's theorem. So the title of the topic for this afternoon will be Superposition theorem versus the so-called Thevenin's theorem. We have bring out an answer by using the so-called superposition theorem or by using the superposition concept. So we will now be checking the validity of that answer by using Thevenin's theorem. We will be solving the same problem. Problem on lesson number 16 will be the same as for lesson number 17. The only difference is that the solution for lesson number 17 will be Thevenin's theorem. It's a check for the validity of the answer on the superposition theorem. Okay, let's proceed. So this is now DC circuit lesson number 17. Okay. The title of the topic will be superposition. We are on the topic superposition, but we are checking the validity of the answer of that superposition by using Thevenin's theorem. So the title of the topic will be superposition theorem versus Thevenin's theorem. From the previous lesson number 16, the current we are looking for is actually the current passing here. It's 1.34 amperes. That is by using the superposition theorem. So for this afternoon, I will be solving the same problem by using the concept of Thevenin's theorem. It's just a check. So we will be solving the same problem. The figure will still be the same. We got a 24 volt here. This is 12 volt. This is a 4 ohm. This is 6 ohm. And connected across this terminal is the 12 ohm. And the problem is asking for the current passing through this 12 ohm load. Okay, from the previous solution, superposition, the current passing here is 1.34 amperes. So by using Thevenin's theorem, okay, we'll try to compute again for the current passing here by using Thevenin's theorem. We are done with Thevenin's theorem. It is just that we are checking the validity of the answer on the superposition theorem. So the requirement here, capital letter I with the subscript all, meaning the current passing to the 12 ohm load using Thevenin's, or meaning Thevenin's theorem. Okay, let's try to bring out the solution. Step number 1. We should recall that there are 3 steps on the Thevenin's theorem. Step number 1. We will disconnect the load that is being considered, right? Meaning the load in which the current will be the one we are looking for. So we will disconnect that 12 ohm load. Okay. Then solve for ETH. ETH is actually TH refers to Thevenin's or the open circuit voltage. Okay, we'll try to disconnect the load. Then there will be an open terminal Then that from open terminal, we will solve for ETH, meaning the Thevenin's open circuit voltage. Okay, so step number 1, we'll disconnect this 12 ohm load here, we'll disconnect. So it's like this. That 12 ohm is gone. So this is an open circuit now, right? So step number 1, by using Thevenin's, we will disconnect the 12 ohm. There will be an open circuit terminal here, this terminal here, and this. And the voltage across this will be ETH, the open circuit voltage, or the so-called ETH, Thevenin's open circuit voltage. Okay? So after the disconnection of the 12 ohm load, we forget for the meantime the 12 ohm load. Later on, we will use that on the final step. We will solve for ETH. And to solve for ETH, we must have to use the so-called, our knowledge on the so-called Kirchhoff's voltage law. Okay? So if this is an open circuit, okay, no load here, no more 12 ohm. There will be an IC here, circulating current. There will be a circulating current. If we try to disconnect the 12 ohm load, there will be a circulating current. And the circulating current could be solved by using, take the summation of the voltages that are Kirchhoff's voltage law. Okay? We'll take this slope here, take the summation of the voltages. So the first one will be plus 24 minus the plus, sorry for this one, this should be minus. Right? A minus to plus, that's a plus 24. There should be a voltage drop here. There should be a voltage drop. So the voltage drop here plus the voltage drop here should be the circulating current times the sum of 4 plus 6. This is 4 plus 6. We combine it already. Regarding this 18 volts here, will it be a plus or a minus? It will be minus, because the polarity of this one is the reverse of this one. If this is plus, okay, this should be minus. So this is minus, sorry for this one, this should be 12 volts. This should be 12, sorry for that. 12. Right? So this is minus 12, and this should be equal to 0. A linear equation, the only unknown is I sub C, the circulating current that will come out if we try to remove the 12 ohm load here. So the circulating current will be a 24 minus 12 will be 12. We transpose this to the right. And a 4 plus 6 will be 10. So the circulating current will be 12 over 10. And this should be with the value 1.2 amperes. Right? So after the disconnection of the 12 ohm load, there will be a circulating current that will come out. 1.2 ampere, the magnitude. And we will be needing this current here in the computation of the open circuit voltage here. It's a must. That's why we computed first for the circulating current. So in the computation of the open circuit voltage, we will be using this 1.2 ampere here. So to compute for the value of ETH, the open circuit voltage, there will be two solutions. Actually, I present two solutions. So for the meantime, if I will try to cover this portion here, I will just consider the left hand side. The loop, the pig configuration will be this. Right? Forget first the right hand side. This will be the configuration. So this should be 24 volts, 1.2 amperes passing through the 4 ohm. The voltage across this terminal here is the one we are looking for. Okay? So again, by using the so-called Kirchhoff's voltage law, take the summation of voltages considering the left side. So it will be, for the 24 volts, it's a plus. It's a voltage source. So this is plus 24. Okay? This is a voltage drop. So the sign here is minus. So the voltage drop here should be the current passing times this 4 ohms. So this times 4. This is a voltage drop. This is minus ETH, the one we are looking for. And this should be equal to 0. So again, we brought out a linear equation in which the unknown is just 1. It is the one we are looking for. So ETH now, we transpose this to the right and we'll try to rearrange. It will be 24. 1.2 times 4 will be 4.8, right? We'll combine these two constants here. We transpose this to the right, then we rearrange. So ETH now will be 24 minus 4.8. So ETH will be 19.2 volts. This ETH is the so-called open circuit Thevenin's voltage. That's the concept of Thevenin's theorem. We'll be needing this one and the computation on the current passing here. Because by using Thevenin's, we are just taking the Thevenin's equivalent, so we could compute for the current passing here. Next solution, it's a check on this 19.2. If we try to consider the left, right loop, we cover this one, consider this one. The configuration will be this, right? This is ETH, this is the 6 ohms, this is the 12 volts, but we must have to place the proper sign of the current passing through the 6 ohm load here. Because the circulating current, for the 4 ohm, the current is like this, right? For the 6 ohm, the current is still like this. So when we consider the right hand side, we must have to place the proper direction of the current. Because when we take the summation of the voltages, if we made a mistake on the sign, there will be a problem. So taking again the summation of voltages, and they should be equal to 0, the right side. Okay? The loop will be this. Okay? So we will start with the voltage source considering the right side. Minus to plus, that's plus 12. There's a voltage here, but will it be a voltage drop or a voltage rise? It's a voltage rise because it's against our loop. So this is a plus. It's a voltage rise. Because just in case the current is going in this direction, that's a voltage drop. But it's against our loop, so this is a plus. So the voltage rise here will be 1.2 the current times 6, the one we computed. The voltage here, of course, it's a voltage drop. So this is my minus ETH, and this should be equal to 0. Again, we formulated an equation, and the only unknown is ETH. So by simplification, we'll transpose this to the right. So it will now be plus. So ETH is actually the summation of this one. Okay, a 12. 1.2 times 6 is actually 7.2, and 12 plus 7.2 is 19.2 volts. So we presented two solutions on the computation of the open circuit voltage. So the first one is correct. We check it by taking the right hand side, it's still 19.2. Step number 3. Step number 2, solve for RTH. RTH is actually the open circuit resistance. When we remove the 12 ohm load here, okay, if we try to get our ohmmeter or multiresistor, we put our multiresistor here. We short the first voltage source and second source. What will be the reading? But we could solve it theoretically. So for step number 2, okay, we short the 24 volts and we short the 12 volts. So if we short this one and this one, it seems this is gone and this is gone. Okay, this will be the location of our multi-tester here. So if we try to draw the configuration, it will be this, right? This is the location of the first voltage source. This is the location of the second voltage source, but we short it out in the computation of RTH. So we are now given a this 4 ohm and 6 ohms. Obviously, their currents are different, so they are actually in parallel. And there are only 2 resistances in parallel. If we try to take the single equivalent of 4 and 6, they are not in series, they are parallel, right? It should be the product all over the sum. That will be 24 over 10, or this will be 2.4 ohms. Okay? Meaning to say, if we try to get our multi-tester here, and we place it here, after the shorting of the first voltage source and second source, what will come out is 2.4 ohms. And that's it. We are almost done in the computation of the current for the 12 ohm load. We will just proceed with step number 3. Step number 3 is draw the Thevenin's equivalent. From the computed open circuit voltage and the open circuit resistance, for Thevenin's, it's a constant voltage source, and the equivalent is actually the open circuit voltage should be in series with the open circuit resistance. Then we'll try to reconnect the load in which the current is the one we are looking for each other, right? So after taking the Thevenin's equivalent, this is the equivalent circuit now. Then we'll try to reconnect the 12 ohm load. And if we try to reconnect the 12 ohm load, it seems the circuit is just a series circuit now. Okay? RTH is in series with this 12 ohm, and we are given this voltage. So if we try to compute for the current passing through the 12 ohm load, it will be ATH divided by the sum of 2.4 plus 12. So I with the subscript 12 ohm should be 19.2, the open circuit voltage, over 2.4 plus 12. And this is 19.2 over 14.4. And what comes out is 1.34 amperes. So by using Thevenin's theorem, we have proven that the current passing through this 12 ohm load here is actually 1.34 amperes. Okay, why I am presenting this second solution? Just to check the validity of our solution by using the superposition theorem. Because if we could not check the validity of the answer from the superposition theorem, we might have made a mistake, and we don't know. But luckily, we didn't make a mistake on the superposition solution, because our current from the previous solution is 1.34 amperes by using superposition. And now to check the validity of that answer, we use Thevenin's. And what comes out is still 1.34 amperes. Okay, that's it, guys. That's the importance of the so-called different approach on how to compute for current passing through a certain part of the circuit by using the different approaches, but we must have to verify the validity of answer. Okay, good afternoon from Los Angeles. This is Professor David.